Okay.
¿Qué tal? Buenos días. Muchas gracias por estar aquí presentes y agradecemos al doctor su presencia. Les presento aquí al doctor David Sánchez de la Llave, el director general interino, para darles unas palabras.
Buenos días a todas y a todos. Gracias por estar aquí presentes. Voy a hablar ahora en inglés por nuestro invitado especial. So it is my pleasure to warmly welcome you to this keynote lecture. Today we are honored by the presence of our special guest, Dr. Rajiv Joshi, whom we warmly welcome to Innowe. You're very welcome to Innowe, Dr. Joshi. And I would also like to thank Dr. Edmundo Gutierrez for his valuable efforts in making this event possible. So without further ado, I give the floor to Dr. Gutierrez to introduce our special guest.
Okay, thank you. I don't know if I need to speak in English or Spanish, but I will do it in English for the benefit of Rajiv. So Rajiv is a senior researcher at the IBM in the Watson Research Center. So this talk is part of the initiative of promoting the semiconductors in Mexico, and is also part of the distinguished lecture program of EDS, the Electron Devices Society of IEEE. So with this talk, we are just opening a window for the promoting the semiconductors. So today we will have this talk by Dr. Rajiv Joshi, which is on predicting techniques, predictive analytics in machine learning. It's basically focused on looking into the reliability issues of advanced CMOS technologies, which are specifically used for artificial intelligence. And this is becoming quite important because as IBM is running one of the main programs on quantum computing. So today, Dr. Rajiv Joshi will be talking a little bit about this on the technical aspects of predictive analytics and also the implications on the semiconductor industry. And I hope you can enjoy this talk. And if you have any questions, feel free to ask them. So we are also connected via, I think, Zoom. So if there are any questions from the audience, we will be ready to pass the question to Dr. Joshi. So without any further introduction, I just want to give the microphone to Dr. Joshi, and please enjoy the presentation.
Okay, can you hear me? Okay, very good. Good morning. And today I'm going to talk about predictive analytics in machine learning. And oh no, you didn't put the. Oh, I just. Oh yes. Okay. Why it's not moving? Okay. So what I'm showing you here is how predictive computing or analytics plays a significant role. And here is this Sumit computer, IBM supercomputer. And what that supercomputer does, it has all these interesting, it can calculate tremendously in such a short time, right? And it came out during the COVID time or Corona time. This identified 77 compounds, which is necessary for creating some vaccination. So this is the power of prediction. So quantum computing is another example people are looking for, that with the power of that quantum computing, you can unravel practically any compound which is very difficult to manipulate by manually. Okay, so that is the power of this. So outline of my talk consists of basically semiconductor trends, areas of growth, challenge of cost, yield, and power, and reemergence of AI, ML techniques and predictive analytics, how it evolved, and application to semiconductor industry, especially logic, memory, advanced technology, reliability, and some of the algorithms that we develop here, okay, and future opportunities. So semiconductor growth trends are really amazing, right? I mean, every technology goes through ups and downs, right? Software, hardware, ups and downs. But without hardware, there is no software. And without software, there is no hardware. Meaning your hardware is very important only when you can build flexible software on it, right? So that is the purpose. Now, if you look at the growth is really tremendous. In terms of billions of dollars, is 400 and beyond. And if you look at the compound annual growth rate, you can see it has, electronic design and automation market especially has grown beyond 14 billion. Let me just do one thing because I'm getting echoes here. So I'm going to my speaker. Okay. Now I won't hear the. So you can understand the power of semiconductor now, right? I mean, all these chip acts are going on everywhere, and all the countries are pushing. Chips are very important. They should be made, in their own country. And America also has, US has Chip Act, which is really flourishing. Now look at the growth again, semiconductor growth trends, and especially look at this bottom line rather than looking at these numbers. AI, machine learning, 5G, IoT servers, cloud expansion, and I need to add quantum here, will continue to drive advanced design at high speed. And we don't see that changing at all. Okay, so keep that in mind if you're looking for, developing your career and in engineering technology, then these are the areas you need to look at. And if you look now in terms of, on the y-axis, the billions of dollars here, and then, number of years here, you can see which areas or which design aspects are critical. For example, memory. Okay, look at the memory. The growth in the memory is really tremendous now. It's right 96, billion to 150 and things like that. So logic is also growing rapidly, but the memory growth is really tremendous because you need to store all your data, and for AI, the large language modeling, all those techniques do need large amount of data. Okay, and it is going to reach quite large number of billions here, as shown here. And then there are other micro components, analog, and all other needs. So why variability? So while we are doing this, we now go down at the bottom, right? It's a bottom-up approach that I'm going to talk about. I gave you an idea where the semiconductor thing is going, but we are marching from technology, and the technology has evolved tremendously. You can see we started with planar FET. Okay, when I started in this field, I started with 1.25 micron NMOS only technology, and bipolar was dominant. I'm talking about 1983, 1984. Okay, so I've seen all in my lifetime. And bipolar was history in 1990 for high performance processors. Then came CMOS technology, PMOS and NMOS together, right? And now it's all about CMOS. And CMOS, we started with this planar transistor. The transistor was invented, in Bell Labs in around 1958, 1960s timeframe. And thereon came Moore's law and the scaling, and then all these techniques, right? Planar FET, then came FinFET. In between, there was SOI, silicon on insulator. That's what IBM was using. And here, this was the bulk technology. The FinFET, because it has 3 sides, you can make gates. And so the electrostatic is much better. Then came gate all around nanowires, okay, small thin wires stacked like this, and gate all over. But it's better to go with the, this, what is called as a gate all around nano sheet, this is called, because it's a sheet rather than a wire here. And the advantages are really overwhelming. So till 5 nanometer, you will see the technologies like, the foundries like TSMC, Samsung have produced up to 5 nanometer, right? This FinFET. And now Samsung is moving, into Intel, Samsung, they're moving into 2 nanometer technology with nano sheet, okay, or gate all around sheets. And that because of the complete, electrostatic advantage, that is where. But when we talk about all these devices, what is the most controlling factor? What are the most controlling factors? Those are process, voltage, and temperature. Okay, we always call this as PVT variation, and which pose challenges for yield and technology scaling, right? For memories and logic. Now, out of that, for designers, what are the important parameters? Threshold voltage, that's the key of a transistor. He cannot change it. Only the process guys can change it. The designer cannot change it. So he gets VT to play with. And he also gets length and the width of a transistor. These are the 3 critical parameters. Other than that, he cannot do anything. And without that zone, he has to design the full chip. So the process, design, architect, there has to be all combination. We call that as a system technology co-design, or architecture technology all co-design. And that is what is getting prevalent in this era of advancement. So these lead to variability. And variability, what it means is that no 2 transistors, the transistor here and transistor here of the same thing, you cannot have similar, meaning it is very hard to manufacture identical dopant atoms in both of them, or threshold voltages in both of them. There is always some variation, and that's what we are going to talk about now. So continuously, so what are the problems? Well, if you look at now the technology, how the technology is going, the amount of investment in the technology is tremendously increasing. Okay, you are talking about billions of dollars. Okay, this is just 10 nanometer node, but here is a 5 nanometer, and here is a 2 nanometer, which is not plotted here. But you can imagine this graph will go up like this, further up like this, bar chart, right? So if you imagine that, then you have to be extremely careful that what sort of yield you are getting. Meaning on a wafer, if you process a wafer, which costs, $20,000, $30,000, $40,000, just for one wafer, 8-inch wafer. Okay, and then you create your design, fabricate your design and create chips, and yield is poor, if only one chip is working, then you are losing big time. That is called as yield loss. And that is what is very critical in this field. And the yield is, if you save even 1%, if you improve yield by 1%, says there are 70 chips on a wafer, and even if you get 5 chips working, then you are increasing your profit by hundreds of millions of dollars. That is the power of this yield. And prediction of this, or building your design in such a way robustly, leads to this talk. So you can see, I will not go into that, why yield is very important. The number of logic steps are increasing, as you can see here, is getting complicated, and estimated yield is dropping, actually. It's dropping, which is not good from the thing, because the complexity increases, and in the complexity, you have to make a yielding product, and that is very tough. It is not very hard, but it takes years. So you need to sustain investment in whatever you are doing. So what is AI and why it is soaring now? Okay, because the AI term was little skeptical, or people were doing, oh yeah, now we are getting into AI. What does that mean? 2008, we knew what we were doing. Actually, we were doing machine learning. Okay, everybody knows what is linear regression is, right? We were doing, all these nonlinear regressions, all kinds of things. But then the data size started growing quite a bit. There was need for algorithms to take advantage of this data and start predicting, and then use this compute power, what we have generated through Moore's law, right? Meaning through scaling, we were able to improve performance, reduce the capacitances, and do magic. Okay, the cell phone that you are seeing is a complex processor. Okay, those who are having cell phones, you can see that that thing can do quite a lot and process. So that power we wouldn't have gotten if we were not working on these these problems. So data is growing, algorithms are needed, compute power has grown, so it's like a feedback loop. So in artificial intelligence is a machine learning techniques. And what is artificial intelligence here? The word became very popular after 2008 or 2000. Everybody, AI. Just even to drink coffee we say AI. Why? Because everybody's in the world is thinking. Now remember, the word AI, the artificial intelligence, came in during the Second World War. Okay, you must have heard Alan Turing. Alan Turing, who deciphered the Enigma code, he was the one who first said that the computers will have intelligence. And this is how it triggered. This is how he started with his deciphering that information on his computer. But anyway, coming back to what this topic, so the machine learning has all these things, right? Supervised learning, unsupervised learning. I will not go into details of this, but reinforcement learning, deep learning. And you can see that these have evolved, very nicely. But these are machine learning techniques. And then if you feed in with the reasoning and understanding or converting your data using the natural language processing into what the machine can understand, and then planning, all these with a feedback loop, then it becomes artificial intelligence. And then there are these machine learning techniques which are very well known and popular. And we were using this, right? I mentioned earlier, even in, in my, undergraduate, way back, we were using, linear regression, this multiple regression, all kinds of things, logistic regression. And now they have become extremely popular because you have too much data. That data needs to be, massaged and, concised or put together in a model so that we can predict in a much better way. So that is the basic understanding of this. And some of these techniques you'll see, and K-means clustering technique, and then this is a known nearest neighbor technique, and support vector machines, which are popular techniques even today. They are used, popularly. Okay, so this predictive technology for nanotechnology, because look at this, accurate yield analysis in nanometer scale design is very critical, and I mentioned why, right? The money is very, everything is expensive. Billions of dollars need to be spent on creating a foundry, and you need to improve the yield. And if you don't improve the yield, you are not going to get the return on investment here. So, and now we are, as we all know, that complex materials and atomic dimensions results in manufacturing variation among neighboring transistors, right? And achieving high yield requires detailed analysis and accuracy in modeling at tail variability distribution. Also, statistics plays a role. Statistics and probability are key here, and multidimensionality for big data analysis in silicon, because we have a lot of data from prior generations of technology. How do we utilize it in generating all this, compute power, as well as, understanding the newer technology? And that is the key lies, and that is the, so extend existing statistical analysis code to a general framework, right? Explore performance enhancements for the code, compare the technique with other regression methodologies, and all other, and put these things on a cloud. So all these things are so critical that we should be able to achieve through some innovations. And I'm going to talk about that now. So coming back to this, the motivation is the cost per transistor is rising and manufacturing yield is critical. So now, as I mentioned about memory, and memory means the array yield, arrays, okay? SRAM memory, you want to call flash, the DRAM, all kinds of things, right? And people are looking this yield always. And then if you plot as a function of transistors, so there are number of transistors here, you'll see. And as you start increasing the cells, in the cells is a 6 transistor cell in a SRAM, okay? There are 6 transistors. So as you start increasing the number of transistors or the number of cells, then what happens is the yield drops, okay? And yield drops as a function of the accuracy that you want, okay? Accuracy meaning you want the yield, say 99.99999, all the way 6 nines. So if you increase the cells, because of the statistics and probability, the variation and all that, the yield drops. So it is very important to make sure that this yield is very critical, and you want to achieve this graph here, which is very hard, but this is what we want to achieve. And then the rising cost of the transistor, which is shown here, you can see it is upward movement. Initially, it started dropping up to 28 nanometer node, and then beyond that, the transistor cost started increasing. So what are the techniques available? What people were doing? So our work started in, around 2000, 2003, 2004, in that time frame. And at that time, everybody was using, Monte Carlo, right? And people realized, I'm talking about people means researchers or foundry owners or, fabless companies, they wanted to make their circuits very robust. How do we define robustness? We define the robustness in terms of sigma, right? We want higher the sigma, higher is the robustness, right? We call this part as Six Sigma part, right? The components in, say, autonomous car need to be designed with Six Sigma. Otherwise, if you design in a short time, the failure, short sigma, like 3 sigma, for example, then what will happen is there is a failure, right? There is a chance. So the lower the sigma, the purity, or that 99, I was talking about number of nines in that 99.99999, they get reduced. So the failure part increases, or failure probability increases. The larger the number of nines, the failure chances get reduced. So that means you want to push it for high sigma, okay? And 6 sigma is a sort of a standard. So that is what we need to do. And so Monte Carlo is popularly used for 3 sigma analysis. And I will explain the deficiencies of 3 sigma. So this is the Monte Carlo. You have 2 variables plotted there. And these 2 variables, what happens is, this is the past transistor, this is the past regions, this is a failed region, and this is a variable 1, VT2 and VT1 for one transistor, okay? And there are multiple transistors, thousands of transistors are there. So you have thousands of these multi-dimensional planes, which cannot be described here, but you can imagine how they look like. So Monte Carlo, now this is the mean here, and this is the phi sigma, mean plus phi sigma, right? So Monte Carlo becomes extremely slow in this region because Monte Carlo spends a lot of time in the passing region. So it doesn't have enough time to go in that region. So that is the reason why it fails. So there are other methods. If you want to talk about, say, sensitivity method, where you add variability in the transistors and go in only one direction, unidirection. As a result, what happens is that method becomes inaccurate because that is not you are overestimating or overkilling your design by going in one direction. You need to cover all the corners, possibilities of all the corners. So this is not possible with this. So it is very inaccurate. There is another method called grid-based method. And the grid-based method is very slow because you divide this VT2 and VT1 into smaller grids. When you do that, the grid becomes extremely very difficult to control, and it becomes very inaccurate and it's slow. So all these methods are not very efficient. Okay, it takes for years. If you have a complicated circuit, Monte Carlo would take for 6 sigma analysis can go up to 6 months to 1 year to calculate. Okay, that's why if you see papers, if those PhD students who are writing papers and all that, who look at Monte Carlo techniques, people who are doing the Monte Carlo and publishing papers, you'll see they only do 3 sigma analysis and a small circuit. Okay, they cannot go beyond because that is the drawback. And some of the techniques which I'm showing you, they are not commercially available, only in certain cases, because we have commercialized them with licensing and all that. So anyway, so what are the techniques which are there for high sigma analysis, right? High sigma is very preferable. I told you why, because you are putting lots of nines, 99.9999 purity, and failure is less. So higher the sigma, less failure. So statistical lead prediction has, MC is the Monte Carlo, then there is a simple Monte Carlo method, there is a variance reduction method, and all these techniques are available. So these marked in yellow, that is where we contributed. That is our contribution. And why none of these techniques are as powerful as these techniques that I'm going to describe to you. And why? Because they are orders of magnitude faster than conventional Monte Carlo. Okay, here is an example. Here is this algorithm. So Monte Carlo, as I said, if you have a Gaussian curve here, right? Our aim to get high sigma is in this region, right? This region or this region. It's called as rare failure event. Okay, I mean, there was a case in automobile industry. There were these bags, airbags, in the during the accident, that those bags will open up, right? So that's made by one company. I don't want to get into the name of the company. And those bags are supposed to open when there is an accident. But those bags did not even open. There was a sheer failure, and there were a lot of deaths, and there were a lot of lawsuits. Now, if they had designed, or I mean, what I'm suggesting is, if they have designed something like this in a more robust way, the chances, again, this is all probability, the chances would have been much lower. Similar thing is also in the transistor region, right? So this is, we are talking about semiconductors. We're not talking about these, these Takata bags or whatever, these airbags. But the idea is the same. So this is the Gaussian curve. So Monte Carlo, spends a lot of time in the passing region here. And in order for Monte Carlo to go here, it takes ages or a year to go in it. And if your circuit is very complicated, okay? Then what we did was, we started with mixture, we developed what is called as mixture importance sampling. So first we start with sampling with uniform function. That is, we take the variables and use the variables in a uniform fashion. So there are thousands of transistors in your circuit. So there are thousands of variables. So we start with that. Once we start with that, as you can see, we find out failure region. Okay? If the failure region is somewhere here, we call that as the center of, we create center of gravity using that region, failure region. Okay? So first step is use the uniform sampling, uniformly sample constant fixed value of that variable, run through the simulations of your circuit, then get the failure mode or failure region. And then from that region, we create center of gravity of failure. Let's see if it is, say, let's assume that it is here. Then we build, what we do is we move the original, the distribution of that variable in this failing region. So what happens? We are automatically in this original rare event region, right? In the tail region. Because we are sampling now in this area. So the new mu, which is this here at the center, is moved to shifted mu here, mu s. And that is where now we are sampling. And then that becomes, this portion becomes importance sampling. So combination of uniform and mixture and importance sampling is mixture importance sampling. This is the way we get closer to the tail region. That is the idea behind that algorithm. So if you look at that and you look these graphs, the speed up obtained from the mixture sampling. So rather than focusing on these, forget about this, that this chart shows that our technique, this mixture importance sampling, converges very fast, while Monte Carlo takes for a long time to convert. Okay, so now if you look at this table, just look at this table. if you want to have sigma, on this side, there is a sigma value, 0, 1, 2, 3, 4, 5, 6. Higher the sigma, better is the accuracy. Okay, this is what I'm trying to impress on you, but keep that in mind. And here is suppose you want to do Monte Carlo alone, Monte Carlo technique. Monte Carlo technique will have for 0 sigma 400 samples, 1 sigma 2100, and if you want to increase to 5, it requires 10 to the 9 samples. While our technique requires only 2300 samples, okay, or around that. And the speed up is of the order of 10 to the 5. Okay, so that is the power of our technique. And that is where you can crunch all your design, complex circuits, devices, all those things in a much, much shorter time. And this gives designer a freedom to optimize his circuit. Once you get the feedback, you can optimize your circuit very nicely and make it robust so that if that circuit goes in your car, in your board, in your car will last a long time. And that is what the reliability also is very important, which is also based on some of these techniques. So normal procedure for this yield prediction is first, step one is a test structure for process variation. You develop your test structure, understand the variation, okay, of the device, build the statistical transistor models, right, where you can define how much your VT is going to vary, 3 sigma. This is how you release, the foundries release the models. We call it as PDK, right? And the PDK is the process development kit or whatever process kit and process design kit, and use that, and that will be used for the designers or students, researcher, whatever you want to call it, and they will design their circuits. So in chip design process, usage of parametric mean and sigma is very critical from step 2 here, and then you prune your variables through sensitivity analysis, and predictive analytics is used on the prune variables, and then design optimization starts. If your design is out of that range, then you give a feedback and start optimizing again. So this loop continues till you get a desired product. So this is how it works. So I will not get into the details of gory details, but I will try to explain that this is a memory, okay? There are 6 transistors here. There are 2 transistors in this inverter, 2 transistors in this inverter. These are back to back. This is the SRAM 6 transistor cell structure. And the idea of SRAM cell is nothing but to read and write, right? I mean, in the memory, what do we do? If we want to store the data, you dump into the memory. You want to read it, right? So this is what happens. So the moment you click on your on a link, it will go down to that, whatever is stored in that link in your memory, and will give you on your screen that particular, location or the site, whatever website, right? I mean, this is how it works. So writing and reading are the most critical part, are the important part of memory, and also retention and the reliability, right? Reliability, how long, that data should be stored there. So now what I'm saying here is that this is the definition of the read stability, because these SRAMs are very vulnerable, okay, to reading and writing, and we have to design it in the domain of variability. So how do we do that? So that is what I'm trying to explain to you here. And so the stability and the writability are the key, as I mentioned. So if you cannot write, initially say 0 is stored on this side, and you want to write 1 If that 1 cannot be written into this 0, then there is a failure. By the same token, if you want to read the data, if you're reading 0 from this side, if you read 1 instead of 0, that's a failure. That's a read failure. That memory is no good for you. Okay? Now, how do you define or how do you design robust memory? So this is what I'm going to show you. And then you can have some design changes. You can apply different voltages to the cell and the word line. Here, cell and the word line, same voltages. Cell and the word line, different voltages. And see which technique is better. So it gives you choices to determine what your choice is, where your choice is correct or wrong. Okay. So here is the analysis done through this mixture importance sampling, which I mentioned earlier, where I can go into that 6 sigma region very fast. And here we have plotted VCS, that is the cell supply voltage, and this VDD, which is the supply voltage to the periphery. You can see that when the word line supply is different than the cell supply, your region of operation of 6 sigma is much smaller. While if you apply same voltage, cell voltage and the word line voltage as similarly, then your region of operation as a function of voltage is much, much larger than this area. So this predictive capability is so important to tell you which design is better, which design is wrong, which design is worse, and all that comparisons. And here, a classic example is, these are the applications. I will not go in the details. So there are lots of applications we cover. We cover all these nice things. But the important factor I want to bring out through this chart is the hardware to model corroboration. Meaning we just did not rely on predicting, but we built chips. We built chips. We also evaluated their values, the failures, the regions, the temperatures, the voltages, all kinds of things. And you can see in this chart, this is the hardware that we built. This is the model that it was predicting. It's a lot of corroboration here. There is a regions it is predicting. There is a trend that you see here as a function of voltages is very close. So it means our model, our predicting capability was verified through hardware. And that is the important factor that we should remember, that prediction is one thing, but we need to have some verification process to validate that model. If the model is not validated and you are predicting anything you want, then it has no meaning, right? It will not work. So that is the idea behind it. That's why we are doing all these electronic stuff, design, working together and trying to create the chips, make sure. But before doing these chips, we need some guiding light. And without that guiding light, we cannot figure out what exactly your yield will be. Of course, hardware is very key, but in the beginning stages, you do not have the hardware. It's a lot of hard work to get the hardware at the end. So here is an application to the DRAM. Okay, the DRAM, what it is, those who are not familiar with the circuits, don't worry about it. But again, the question comes back to back here is if I plot sigma values, and remember again the definition where I'm pushing is higher the sigma, better it is, right? 99.99999, like that. So higher the sigma, better it is. So if you plot the read bit line, that is from the DRAM, you're reading the data, and you're plotting the read bit line discharge. The bit line will be discharging at certain time the output is finalized or output is sensed by the sense band, then what happens? So for the read 0, which is labeled here in this, for read 0, it drops down, the yield drops down as a function of discharge time. But on the other hand, if you're reading 1, the data is just opposite, meaning the sigma improves as a function of discharge time. So what is the optimal value for reading 1 and 0? So this technique, our yield prediction technique, gives us this range, optimal range. So this is what we learn from these predictive analysis. Okay. I will not go in these kind of circuits. They are similar. We are trying to optimize transistors, trying to optimize designs, all kinds of things in there. Do you know how much time? Oh, I have 50 slides more. No, I will cut it down. Okay, meaning I know. Okay, so, I want to give you a little bit of idea about the TCAD. Okay, the TCAD is something, is called as technology CAD, and those who are working on the technologies or devices especially, this TCAD is very important because you need to understand where the sources of variations are. And using this technology, this process, we were able to do look at what are the important variability issues through design. Okay, and one of these things is line edge roughness. This is metal grain granularity and random dopant fluctuation. And this is the total, VT that we observe, sigma variation through simulation, and this is through hardware for verification, as I mentioned, right? So if you look at now, why is metal is used, right? Why is it used now? Metal is used to control the VTs now, right? The new trend is to have different kind of, titanium nitride, tungsten, and variation in that. All kinds of things are used to get different VTs. And the VTs are important for the designers, right? To reduce leakages, performance, increase, all these things are so important, right? So if you look at that, and if you look at the random dopant, fluctuation, the random dopants are in these technologies now, your 5 nanometer, 2 nanometer, all these technologies, these dopants are now of the order of 3 or 4. 3 or 4 atoms inside that channel, okay, device channel. It's very hard to make 2 devices identical, right? So there is always variation. And if you, this random dopant fluctuation is the parameter. Now look which dominates, which variation dominates. And this is nothing but metal grain granularity, which is dominating here. And if you compare with the simulation results that we got, that we observed, and through hardware, there was only 10%, 12% variation. So our predictions and our hardware data are very close. And this is where the modeling efforts are so critical here, right? Okay, so I will skip this. There is one thing we were able to do also using the capacitances through using TCAD, right? So FinFET technology was used, and we were able to construct a 3D structure like this, and we were able to understand the capacitances, all the reactions, interaction between the top layer, bottom layer, here. This is the device. These are devices here, and capacitances are very critical because you are going to simulate, right? In the simulations, SPICE simulations, spectral simulations, what you need is this accuracy in capacitances. And this is what we were able to do, that we were able to accurately predict these kind of things using these predictions. And then we were able to predict the yield of the FinFET cell before FinFET became or came into production. So that was our contribution, meaning with understanding these capacitances, generating higher accuracy, modeling those those effects, we were able to do, and we were able to show how the writability, read, yield, all these things are critical for 14 nanometer cell. Okay, this is another example of the yield. I will not go through this. And okay, so the reliability I want to show you, reliability technique. Okay, so in reliability, as you know, humans age. We all know that, right? That's normal. But transistors also age as a function of time. As a function of time, humans also, age, right? We go older, right? Meaning, although physically we look young, but our body goes, you know what I mean. So aging is, universal rule. So what do we do, if the transistors are aging, and you don't want to have a situation where, say, I work for IBM, and our chips are in mainframe where they are used in banking industry, and all of a sudden somebody's account disappears because of malfunction of a chip. Then there is lawsuits and all those things will go on. You have to be extremely careful. So you have to design your chip robustly. And this is what I've been trying to say here. And this is, again, why I'm talking about the memory all the time is because memory occupies 60% of your processor. Okay, 60% of your processor, 50 to 60%. Okay, so at the end, there are a variety of mechanisms, failure mechanisms using aging, reliability, right? So I will not go in that, but I want to show you a chart because of the time limit here. Okay, so using these algorithms, you can predict beautifully these contours, okay? All these contours as a function of voltages, which is on the cell voltage, and this is the peripheral voltage of your chip. Okay, cell meaning SRAM cell. So what happens is these dots you see here, pink dots here, everywhere. These are hundreds of chips measured, okay, here. Using these conditions, and we determine, okay, their sigma, these color zones that you see are the sigma values predicted by our algorithm. And here is the best sigma, and here is the worst sigma. Okay, this label has to be opposite, but you can just imagine blue color is the best, and this is worst. So we measure, and this is the V min, that is lowest voltage a chip can attain. And how we did this? Well, we measure hundreds of chips. We measure hardware V min, and then we plotted here for each voltage combination. And they fall very closely in this colored region that you see here perfectly. And amazingly, the corroboration between, good corroboration between end of life of this chip in the reliability zone, okay, with repair yield, showed excellent corroboration. That is the point I'm trying to make. That look, these points really fall in this region, and those chips were predicted, meaning that their operation through these voltage combinations were predicted by this mixture importance sampling algorithm. So this is the power of predictive analytics. That is the purpose of this talk. This is what I wanted to show you. And then we developed many algorithms, future algorithms, recent algorithms, they are there to improve even that 10 to the 5 orders of magnitude improvement we made it up to 10 to the 6 orders of magnitude by using these additional techniques called sparse regression. Then, I will not go in, there is a lot of, I'll have to sit here and talk a lot, but just to give an idea. And there is another technique called logistic regression. That is also another example that we did. And it has been, we were able to get substantial improvement in this predictive capability. Okay, I want to just give you an idea of what we did and where was our impact. So used in IBM chip design process, whatever I described to you is all there and fully validated. We also commercialize these techniques. This is applied to this supercomputer, Power 9 series, Power 7, then Watson system that IBM built, those chips which were used here, and all these good things which we are proud of that it really went in. And finally, I want to summarize in a in detail that semiconductors are approaching atomic and economic limits, and variation are greater at atomic scale, so yields are lower. Okay, predictive analytic techniques are a fundamental part of chip design and becoming increasingly important. And we demonstrated some of the applications, ideas here. And also I want to bring out that there are future opportunities abound, okay? That is predictive failure analytics outside semiconductor industry, such as finance, data and trend analysis, medical applications can be used. Same techniques. Actually, we have not published this result, but we have applied this to portfolio management, this technique, like, rare failure event. That is, when you predict something, it shouldn't go wrong, and your accuracy, like you are managing your portfolio. So all these techniques are also can be done. So it has an extended usage, sort of, and that's the point I was trying to make. And and then all these things are now into cloud computing services, and there are further opportunities through EDA for cloud computing services and fabless semiconductor industry. With this, thank you very much for all your attention, and thank you very much again.
Okay, so now we open the session for questions from the public. There is one over there.
Thank you, Dr. Rajiv, for your lecture. I found it very interesting. I'm in the field of IC design, so I was wondering if, to your knowledge, if EDA providers like Cadence or Synopsys have already implemented some of these predictive analytic techniques inside their softwares?
Yeah, so excellent question, actually. So I talked to you, I told in my talk that this technique, we started in 2004. At that time, nobody was using it, right? So we went, people came actually, EDA companies came to us for commercialization. And we sold it to a company which also licensed to many other, I don't want to get into the names for specific reasons, to many semiconductor foundries. They're using variation of this. And companies like Cadence, Synopsys, Solido, Siemens, they are using such techniques already.
Okay, thank you.
Because that became the, we got, our paper is cited, we published the paper in those days. And after that, we did a lot of work as well. And that was highly cited paper in this domain.
Thank you very much.
Any more questions? I have one. So I see that the topic is quite complex. So I can imagine how many people is involved in this project. Can you tell me how many people is involved in this project of developing the statistics predictions?
Meaning in IBM?
Yes.
Oh, IBM, actually, you'll be surprised. We were, team of only 3 people. I was heading that. Yeah, but then it became because all the designers started using it, right? It became POR, or process of record. So then we have a couple of, meaning it went to our EDA guys, and then they employed support for this, because then because we are in research. Once we transfer the technology, then they don't need us, right? Meaning we can move on to do something else. That was the intention. But industry really picked it up. I mean, a lot of papers you'll see after that variability, came about.
Okay, okay. There is one question there, Daniel.
Okay.
It works, I think.
Okay. Here it is. Here it is. Okay. Sorry. Thank you very much for the really nice talk. The question is a little bit more about what is your expectation? What is in which direction is the semiconductor industry moving? This kind of all these examples of the amount of work and the amount of effort that's being put into the reliability discussion and the predictions and everything shows us, together with the problem of power consumption in the new microprocessors, and also the costs of the foundries going further to 7 nanometers, 5 nanometers, 2 nanometers right now, going from $4 to $5 to $6 billion. And that for the first time, as you showed us, the expenses are not going down with the increased number of transistors. So each transistor is actually costing more. So what is your prediction? Where is the semiconductor industry going? So you showed us that 28 nanometers apparently seems to be like a really nice compromise between all these factors. And what we know is that in frame of the European Chip Act, for example, there was this big plan of constructing many new foundries in Europe that now are stopped. For example, in Dresden, from Global Foundries, they were going to the 7 and to 5 nanometers, and then they stopped for internal reasons. And we have this in Arizona also going in this direction. But do you see that this is the way to proceed? So is the semiconductor industry really going in that direction? Or maybe it's time to revise again and try to see what is the best, let's say, trend or the best technology to be pursued? Maybe more than just going into the Moore's law and making every time more expensive, more problematic devices on a really, really small scale. So what is your opinion about this? Where are we going, basically? Thank you.
So, I mean, bottom line is, I mean, your question is, okay. To me, okay, the scaling has practically, stopped. Okay, meaning it's very difficult. That leads to tremendous amount of investment, okay, in order to do these things, right? But the innovations have not stopped. Innovations have no boundaries. Okay, so if that is the case, people are going now in the direction of, chiplets, okay, for the yielding. Then also the 3D, okay. Then there is a lot of, now the packaging industry is evolving. In those days, the packaging industry was so backward, only scaling, right? Now the packaging industry is at the front runner here. So there is a lot of development you will see. Photonics, okay, is also a very interesting one. How to combine these, meaning utilizing heterogeneous structures. You can combine. And this is where we are heading. I mean, you'll see a lot of, I mean, just on Tuesday, we had this IBM CAS EDS symposium that I run. And we have these invited speakers and all. It's a one-day symposium. It's free, open to everyone in the world. I wish you guys had known this, but if you are joined, there was a link set up. All these speakers, we had, and which points only in that direction. Okay, and that's how it is moving. And people, will come up with ideas. I'm not saying. So if you look at only Moore's law in that fashion, then we have some issues. But if you think more in terms of number of transistors, then bigger and bigger Moore, because now there are there are trillion transistors now on a chip. It's just amazing, right? People are already using HBM, right? 4-layer, whatever. Now they are talking about building it like skyscrapers. Similarly, other memory units also will go up, things like that. So that's my viewpoint.
Okay. Any other question from the audience? I think I have one, but I will reserve it for the lunch time. So, okay. If not, I think we are done with the presentation, and so we have a present from Inaue to you, Rajiv, and thank you for listening to this conference, and thank you everybody. Thank you, Rajiv.
Thank you very much, Dr. Joshi, for this wonderful talk. And well, we'll have a small present for you, and this recognition, which I will read. And it says, this certificate of appreciation is hereby granted to Rajiv Joshi in recognition of his valuable contribution as a speaker in the conference entitled Predictive Analytics for Nanometer Technologies in the Initiative for Promoting Semiconductors conducted on November 22nd, 2024 in Santa Maria Tonantzintla, Puebla, and it's signed by the Interim General Director of Inaue. Thank you very much, Dr. Joshi.
Thank you. Thank you. Thank you. Thank you very much. Thank you very much. Thank you very much. Thank you. I know that. I didn't realize how much, what is the, sorry, what is the meaning, the audience, and how many, so I could have, meaning that's fine. Oh, okay. Okay. But they didn't ask any question? No, they didn't. This is yours. No, it's here.